to introduce Dr. Shiroman Prakash. Dr. Shiroman Prakash obtained his PhD in theoretical physics at the Tata Institute of Fundamental Research, focusing on string theory. He has a bachelor's degree in physics from Johns Hopkins University, where he received Provost Award for undergraduate research. A master's degree in physics from the Indian Institute of Technology, Kanpur, where he received awards for best academic performance and best project work. He is a faculty member at the Physics and Computer Science Department of the Aalborg Educational Institute. It's my pleasure to welcome Dr. Shiroman Prakash for his presentation.
Thank you very much for inviting me to give the talk. The title of the talk is Quantum Mechanics, Gravity, and Strings. So, extremely successful quantum theories exist for describing elementary particles and their interactions via electromagnetic and nuclear forces. However, combining quantum mechanics with gravity, which is understood as the dynamics of space and time in Einstein's theory of general relativity, leads to serious technical and conceptual difficulty. And despite the fact that direct tests of any theory of quantum gravity seem out of reach, the problem of quantum gravity is one of immense theoretical interest. Quantum and classical theories cannot coexist consistently, so all forces, including gravity, must be described by quantum mechanics, or else quantum mechanics must be modified. I'll give a short summary of the problem of quantum gravity, in particular focusing on the black hole information loss paradox, and finally I'll tell you why string theory is probably an in-principle solution to the problem of quantum gravity. So what is quantum mechanics? We've all seen the double slit experiment. So the idea is shoot an electron through two slits and see what happens, and you find that the electron behaves like a wave, in the sense that if you shoot an electron through this two-slit experiment many times, you'll see an interference pattern characteristic of wave-like behavior. And of course, if the electron is a wave, then I mean the wave-like behavior arises from interference between the two paths that the electron could have taken, which in turn implies that you can't answer the question which slit did the electron go through. And more precisely, what the idea is that there's a notion of complementarity. Either you see an interference pattern, or you can ask which slit the electron went through. But if you try to answer both questions with complete certainty, you'll run in. You won't be able to do it. Just so you can generalize that more to quantum mechanics to general systems, and the basic postulates of quantum mechanics can be stated as follows. Say you observe an electron at point A. At time t later, you choose to carry out an experiment to determine whether or not the electron is at point B. This is the input from the experimenter in choosing what experiment to set up. What quantum mechanics tells you is you sum over all possible paths which the electron could have taken connecting A and B. With each path, you associate a phase, and these phases add and interfere to give a probability amplitude which you mod square, and to get a distribution just as in the double slit experiment. Okay, finally, nature chooses the result of your experiment randomly according to the calculated probability distribution. So quantum mechanics tells you how to calculate probability amplitudes, but you have to first tell quantum mechanics what probability amplitudes you want to calculate. Okay, by choosing what you want to observe. And some might object that, okay, well, what's described in the last slide and also in Vishal's slide might overemphasize the role of the observer. I won't really address that here, but this is some quotes from Niels Bohr. So in our description of nature, the purpose is not to disclose the real essence of phenomena, but just to track down as far as possible relations between the multiple aspects of our experience. And regarding the fact that ultimately there's a choice of what to observe, which is required to specify mathematically precisely specified quantum mechanics. I mean, we have to make a choice between the different complementary types of phenomena we want to study. But okay, I'm not going to discuss too much about this here, so I suggest reading von Neumann's book on quantum mechanics and also the work of Henry Stapp for more on this. But okay, despite their perhaps intrinsically subjective nature, quantum theories make extremely accurate predictions of experimental observations. The list of experimental tests of quantum gravity is very long, but the most well-known example is the electron's magnetic moment, which can be calculated using quantum electrodynamics, which is the quantum theory of electrons, positrons, and photons. So the electron's magnetic moment is given by this formula, which is parameterized by a parameter A sub E. It's A sub E is small but non-zero and is determined by P2ED calculations, which are straightforward in principle but tedious in practice, and they just depend on one parameter, the fine structure constant alpha. So as far as I know, the best measurements of the electron's magnetic moment were carried out by a group led by Gerald Gabriels at Harvard, which determined A to be about with a relative uncertainty of about 0.25 parts per billion, and the techniques used ion traps, which may be similar to the realization of quantum computers. So the QED was in fact tested much more stringently than inventors could have ever envisioned, as Freeman Dyson said to Gerald Gabriels. As one of the inventors, I remember we thought of QED as a temporary and jerry-built structure with mathematical inconsistencies, and we normalized infinities swept under the rug. We did not expect it to last more than 10 years before some more solidly built theory would replace it, and we expected and hoped that some new experiments would reveal discrepancies that would point the way to a better theory. But nevertheless, QED is very successful. But what are the new experiments that we use to study the fundamental forces and quantum mechanics? And the main experiments that physicists carry out, that the high energy physicists carry out, involve the scattering of elementary particles, such as those which happened at the Large Hadron Collider. Okay, so the basic idea is you collide a system, you consider a system of, okay, not non-relativistic particles, but you consider a collision of many particles which initially are infinitely far away from each other and hence non-interacting. Each has a well-defined energy and momentum. The particles then collide, and we don't know what happens in between, where we use quantum mechanics. But long after the collision, the system again consists of one or more outgoing particles, infinitely far away from each other and non-interacting, with a well-defined energy and momentum. So a typical scattering element experiment has many possible outcomes. The total number of outgoing particles may be different from the incoming particles. The types of particles may be different, and the energy and momenta of each individual particle may be different. But the idea is we want to predict the results of these experiments. We want to define a matrix called the S matrix, which lists the probability amplitude for each possible outcome as a function of the incoming particles and their momenta. Conservation of information implies that S matrix is unitary and vice versa. And though S matrix really only describes scattering elements, in principle we would think it encodes nearly all conceivable physical experiments one can carry out, at least. Okay, S matrix elements are calculated using a sum over paths, similar to what I said, just in this case, a sum over Feynman diagrams as pictured. And each diagram contributes to the probability amplitude, which we then square to obtain the probability of a given outcome. So although we can determine the final states and the initial states, we cannot determine what happened at intermediate times any more than we can determine which slit the electrons went through after we observed the interference pattern. So since all we're interested in is the initial and final states, there was an approach in the 60s, which is described here, that because there was an ever-growing list of strongly interacting particles, the idea was simply to just define an S matrix telling you the results of scattering experiments, and forget about any underlying quantum theory in which you would derive this matrix. Of course, it turned out that the forces are described by a quantum field theory which has a bit more content, and that all forces are actually described by not only an S matrix but the quantum field theory, and a quantum field theory associates one or more abstract observables to each point in space. So an abstract observer located at X can, in principle, measure phi of X anytime, any number of times according to his or her subjective choice, and that's perhaps a bit more than what you might. And a priori, that seems like it's more than an S matrix, but in practice, when we test quantum field theory, we just derive an approximate S matrix for the quantum field theory and compare that to the results of scattering experiments. So all the fundamental forces are ultimately described by quantum field theory, except for gravity, and in practice, their tests are some of the strongest experimental tests are simply scattering experiments. So where we predict the probabilities for final states given the known initial states. Unfortunately, gravity is harder to deal with. So general relativity tells us that gravity describes the dynamics of space and time. A quantum theory of gravity would, in principle, have to be a quantum theory without time, or at least drastically alter our notions of space and time. And we can make this more precise by considering the predictions of classical general relativity and quantum mechanics when we study black holes. So black holes are things which exist in space. For example, there's an X-ray source in the galaxy called Cygnus N1, which is probably a black hole, and of course, and was the subject of a wager between Stephen Hawking and Kip Thorne. So, ultimately, I mean, black holes exist. I'll tell you what the black hole is in a minute, but black holes exist in the sky, but how do you know if some astrophysical object is a black hole? Because you can only via indirect measurements of light coming from nearby the black hole try to rule out all other possibilities that it's not a neutron star, it's not some other object, and convince yourself that the densities of matter and energy are so high that a given astrophysical object can only be a black hole and nothing else. So there's always some uncertainty when you observe a candidate black hole in the sky, and Stephen Hawking wagered that Cygnus X1 is not a black hole, and Kip Thorne wagered that it is, but it turned out that it is, so Stephen Hawking lost that wager. Okay, so what is a black hole precisely? If enough mass is placed in a small enough region of space, a black hole will form. More precisely, that there will be a black hole is some gravitational object that there's a critical distance from which the escape velocity from that object becomes greater than the speed of light. And special relativity tells you that no object can travel faster than the speed of light. So an analogy for a black hole is, if, in terms of just easily understandable physics, is consider fish swimming in a stream of water such that no fish can swim faster than a speed c relative to the waters. If the velocity of water changes with location, like near a waterfall, then you can imagine so if you have a velocity distribution such as this, a fish swimming here can swim up to here, but also swim back, because the fish can only move can only move at a speed c relative to the water. But if once the water is moving in a given direction faster than the speed c, then there's no way a fish can swim back from where it came. So there's a critical point of no return where the velocity equals c, as should be obvious from this diagram. So since it's not even light can escape a black hole, there are effectively one-way surfaces in space-time that absorb but do not emit. Okay, in the 1970s, Hawking discovered that black holes in a quantum theory must radiate. Okay, the reason is that, heuristically, in the vacuum of a quantum field theory, pairs of particles and antiparticles continually pop into existence and then collide and annihilate each other. However, if a pair of particles pops in and out of existence very close to a black hole, then one might fall into the black hole while the other escapes to infinity, and then that becomes a source of radiation. So, and even just on general grounds from Einstein's A and B arguments, you know, in a quantum theory, anything which absorbs must emit. However, all black holes of a given mass, charge, and momentum are identical. Hence, radiation emitted from a black hole is independent of the matter and information that form the black hole. Moreover, it turns out that the radiation is thermal with a temperature that depends on the mass of the black hole. As the black hole emits radiation, it loses energy and mass and becomes smaller till it eventually evaporates, leaving behind a universe filled with thermal radiation, and in which case all information about the matter that formed the black hole is apparently lost. So this is a contradiction with quantum mechanics, in which necessarily preserves information and leads to a bit of a debate. So people who spent their life studying general relativity believe that indeed information swallowed by a black hole would be lost, whereas people coming from particle physics backgrounds who study more quantum mechanics believe that information would have to be preserved somehow. In particular, there's a famous wager between Stephen Hawking and Kip Thorne, who are general relativists, and John Preskill, who's a quantum field theorist and quantum information theorist, and the wager goes as follows. Whereas Stephen Hawking and Kip Thorne firmly believe that information swallowed by a black hole is forever hidden from the outside universe and can never be revealed even as the black hole evaporates and completely disappears. And whereas John Preskill firmly believes that a mechanism for the information to be released by the evaporating black hole must and will be found in the quantum theory of gravity. Therefore, Preskill offers, and Hawking/Thorne accept, a wager that when an initial pure state undergoes gravitational collapse to form a black hole, the final state at the end of black hole evaporation will always be a quantum state. And the loser will reward the winner with an encyclopedia of the winner's choice, from which information can be recovered at will. And this bet was in 1997 at Caltech. So how can we resolve the bet? So experimental tests of quantum gravity are impossible. Even Hawking radiation can't yet be observed. But the question is it theoretically possible, even in principle, to define a quantum theory that has gravitational interactions in its classical limit, but is otherwise a unitary quantum theory. And for and it turns out that such a theory does this, which is called string theory, and I'll describe it now. So string theory is based on the assumptions that instead of particles, the elementary excitations of nature are string-like objects. So a particle traces out a world line in space-time, and hence a string would trace out a world sheet in space-time. Quantum mechanics of strings are described by sum over world sheet, where to calculate the probability a string would be observed somewhere else, we sum over world sheets from the initial string, or more precisely, different vibrational modes of the string correspond to different elementary particles, but interactions are described by a sum over world sheets which can merge and split, just like Feynman diagrams. So, okay, remarkably, for reasons I won't discuss, gravitational interactions automatically emerge from the sum over world sheets. And there's a price to pay for defining a consistent sum over world sheets, in the sense that one needs extra dimensions and supersymmetry, but as a matter of principle, the question is, can we define a unitary quantum theory that includes gravitational interactions? So the point is, the sum over world sheets defines a unitary S matrix, which allows us to predict the probability amplitudes for any scattering experiment in this quantum theory, which includes gravity. So that means if string theory is correct, we should be able to use it to predict outcomes of a collision of any number of particles with any energies. In particular, we should be able to consider initial states with enough particles and enough energy to form a black hole according to classical gravity. String theory would predict that the probability distribution for different outgoing particles would predict the probability amplitude for different outgoing particles, which would be like Hawking radiation, but not quite, to be observed in the far future after the black hole would have evaporated. However, the prediction must preserve all, for the outgoing states, must preserve all quantum information about the initial state, because this S matrix defined by string theory is unitary. So this is an in-principle answer to the question of quantum gravity, and what is a more physical interpretation of it? Gravity is the dynamics of space and time. So since the sum over world sheets includes gravitational interactions, it also can be thought of as including a sum over all space-time geometries interpolating between the initial and final states. Of course, in the semi-classical limit, one would expect only the space-time geometry containing a black hole to dominate the sum over space-times. But calculations involving in the 90s showed that actually contribution from other space-times without a black hole do have a contribution to the sum over space-times, which is non-negligible on timescales long enough for the black hole to evaporate. So the basic idea is just like in the two slit experiment, to predict the results of observations, we have to sum over space-time geometries. Those with a black hole and those without a black hole, to predict the outgoing particles we see after a black hole evaporates. And this argument actually convinced Hawking that information is preserved, and he conceded his bet to John Prescott. So in his own words, he says that black hole formation and evaporation can be thought of as a scattering process. One sends in particles and radiation from infinity and measures what came back out to infinity. All measurements are made at infinity where fields are weak, so one never probes the strong field region in the middle. So you're never sure that a black hole forms, no matter how certain it might be in the classical theory. And the confusion and paradox arose because people thought classically in terms of a single topology for space-time. So it was either a flat space or a black hole, but the Feynman summary histories allows it to be both at once. One can't tell which topology contributed to the observation any more than one can tell which slit the electron went through in the two slits experiment, although that an observation at infinity can determine is that there's a unitary mapping from initial states to final states, and that information is not lost. So this is Hawking's ideas, but everyone isn't convinced. Kip Thorne, for instance, hasn't conceded his bet, and people like Penrose certainly aren't convinced. But nevertheless, the solution convinced some people, but it's a solution for an observer outside and very far away from a black hole. So it predicts what an observer outside a black hole would see, and it gives a prediction consistent with what we expect for classical general relativity in short timescales, but over long timescales, it's also consistent with unitary quantum mechanics. But it's a solution only for an observer outside the black hole. So you might ask the question, what does an observer who crosses the event horizon and falls into the black hole see? And from classical general relativity, you should see nothing as you cross the event horizon. You only reach problems when you hit the singularity. But it's not obvious what would happen in a quantum theory. Perhaps some people have suggested that any observer who crosses the black hole event horizon, even before he reaches the singularity, would be just, burnt to a crisp even as he crosses the event horizon, which would be a new quantum effect in places where we don't expect quantum effects to be relevant. That's not very good. There could be other possibilities, but you might say it's not even a sensible question for a scientist to ask. Just like no one asks what does an electron see as it goes through the two-slit experiments, and in fact, even if you do send the astronaut in and let him fall into a black hole, you'll never be able to report the results of his observations back to you. So it's like asking what happens after you die. It's not a question the scientific community can a priori know an answer to, but it's a question an individual observer would know an answer to, and it's a growing question, and that's probably why people aren't convinced. But however, it's still better than nothing, and sort of a small victory for quantum mechanics over gravity. And whether Pascal himself is satisfied with the argument, he accepted his prize, which was an encyclopedia of his choice, and that's the 8th edition of Total Baseball, the ultimate baseball encyclopedia, which is an American sport similar to cricket. In case you haven't heard of this, okay. So that's it. Thanks. Yeah, so that's it.
So it is right to say that Hawking, in some sense, is saying that, quantum mechanically, you cannot be sure that black holes are formed. So, is it denying the existence of black hole itself, or because if that is so, then that trivially will, if there is no black hole, obviously there is no information loss paradox. So, is that trivial, or what are you saying?
It's like saying that if you shoot an electron through two slits, you don't know which slit and you observe the interference pattern, then you don't know which slit the electron went through.
Right.
So he's saying that, we'll make observations of a black hole from far away. We'll get, radiation and stuff. The radiation would look like there's a black hole if you don't look very carefully, but if you look carefully, you would find that it contains two contributions, one from a universe with a black hole, one from a universe without a black hole, and they interfere in a way that preserves the information.
Right.
So it's not really, I guess it's saying that, you don't know if there's a black hole unless you actually go in. That's what he's saying. It's not that satisfactory, I guess.
So if there is a contribution from the space-time sheet where black holes do exist, so there will be some probability of existence of black holes that will contribute to something, right? So there may be, information loss with some probability that can happen, right? If there is contribution, like if you send electron through both the slits, You have one amplitude coming from one slit, another amplitude from other slit. So
Right, so they both contribute to the
Both
probability
contribute.
amplitude, but when you consider both contributions, you get a result consistent with preservation of information. If you consider just one contribution, you lose information.
Yeah, right.
That's the answer. It works for an observer outside the black hole. It may not be satisfactory if you actually send an observer into the black hole. That's why everyone isn't happy with it.